to get started. I am very, very pleased that my colleagues at University of Chicago Center for Spatial Data Science have been able to join us today. I am Diana Sinton. I am the Executive Director of UCGIS. And we are super pleased to be able to have this workshop and to be able to offer this to our participants. Let's see, I am going to be troubleshooting different types of problems that come in, like people who can't hear audio. I'm getting a couple of questions like that might come into the questions. I'll be working on that. The best thing to do, if you go up to the file menu and look for preferences and then audio, but more of the problems with GoToWebinar's audio will be addressed if you leave and then come back in. You'll see. Other questions will be addressed about workshop content will be addressed by our workshop presenters. I'm going to now turn it over to Dr. Marinia Kolek, and she will take over from here. And thank you very much.
All right, thank you so much for Dr. Sinton for having us here today. I will briefly turn my camera on just to say hello. We're going to mainly have cameras off to kind of ensure that we are, let me pull this back here, to ensure that everything is working as it needs to be and there's no Wi-Fi bandwidth issues and that sort of things. So thanks for being here. So today we'll be talking about an introduction to GIS and spatial analysis in R, but using an application-driven approach. And so I'll be one of your facilitators. I'm a health geographer based out of UChicago, was in the ArcGIS world for probably a decade before switching over to open source. So so hopefully that is, I'm the kind of native GIS person in our group here. Ching-Wing Lin is a postdoc at the center and more of a recent GIS convert, I hope. Her training was in causal inference and kind of social network analysis and that sort of thing. And her background is in R as well. So she brings that with us, or with her, to our program. And then finally, Moksha Mangani, who, and Moksha, if I'm mispronouncing your last name, please correct me. She is a graduate student at University of Chicago and also was really integral to developing this work, the toolkit. And before we dive into the workshop itself, it helps to provide a little bit of context. So we're working from this toolkit. This is the Opioid Environment Toolkit. If you don't already have a link, access to this link, we can drop it into the chat so that you can access it directly. So this is a toolkit that was essentially developed for a research network studying the opioid risk environment. So this is part of the Geocoding network, which is, there's all these acronyms here, but essentially part of NIDA, which is the National Institute for Drug Abuse. And one of the core centers for methods and advanced analysis is based at UChicago, and our team leads up the spatial analysis core of that. And always getting a lot of questions of a lot of people are interested in doing GIS and spatial analysis, but they, transferring the skills from their backgrounds to GIS may not be that obvious to them, right? So our goal is to really expand GIS knowledge across different disciplines, scale up analysts who may already know R or coding in other environments, but then also the flip side, which I'm really passionate about, is expanding our capabilities across GIS networks. So I've met a lot of people from kind of the traditional GIS kind of point and click based systems who are interested in learning how to extend that to R or programming languages. But it seems like that learning curve is really massive and potentially intimidating, right? And especially if you've been doing GIS for decades, being uncomfortable and launched in this kind of new, this new space can be a lot. So our goal is to help onboard that process from either direction. And also this toolkit is really kind of coming from a perspective of to better address challenges in some of the traditional point and click GIS out there. So oftentimes there may be interest in doing GIS, but there may not be the cost to afford someone with this so if there is a specific proprietary brand being used for GIS, being able to find the right individual to work with that. Or on the flip side, you may have a group of analysts, but who are eager to dive into work, but the cost of a proprietary tool may not match that. And then finally, one of the core reasons why a lot of us who are passionate about open source GIS do so is to advance reproducibility and scale up some of the things that we do. So yeah, that's my very short intro about that. I'll try not to bore you further. But at this point, we do hope that everyone has at least installed R and hopefully RStudio. So the process for what we do when we're starting to work with this is, again, 1, install R, 2, install RStudio. We'd already provided a couple different links to that. But then the next step would be installing packages. And this is really where you'll learn whether or not you are going to clear the first hurdle that often first-time users will experience. And it's not necessarily first-time users. Like when I get a new computer and I have to totally reinstall my whole coding environment, I may also have to troubleshoot for a little bit to get things right. So to install packages, once everything is, your R and your RStudio is refreshed, these are the code snippets that you would just enter into your coding environment. If those install successfully, the next step would be to load the packages. And Moksha in a minute will be kind of highlighting some of this as well. If you're able to load these 2 libraries successfully, from my experience, you're good to go. That means that the biggest hurdle of getting your it's often not the RStudio environment that provides that can generate hangups. It's usually specifically some of the spatial libraries because they're, as you might expect, a little bit more complex and advanced. So when in doubt, if this step doesn't work, what is done in R is a little bit different than other GIS systems. In our case, one of the best ways to resolve errors is by copying copying the error that you get in R and pasting that into Google search to kind of to look for others who have had similar errors. And what you will find is that solutions will tend to kind of bubble up to the top of the Google search term, or to the Google window. So very, very briefly, some kind of tips or potential hangups or tips that you may experience, that I've experienced in the past. If you're wondering about what R version to use, using the latest R versions should be successful. So this is only going to apply if you're working with a very old R version. We recommend at least minimum 2, but doing a more recent one is much better. Also, there can be issues related to RGDAL or raster. I will copy and paste this issue right here. I was just loading R and RStudio on an environment this morning and ran into this. So I will copy and paste this. This is well, when you look at it, you'll be able to check it out. And then other things are going to be similar to to what some of you have experienced in ArcGIS. So in ArcGIS, when something doesn't work, sometimes closing it down and restarting it will fix it. So restart as needed is also a really helpful tip when you're if you ever experience any installation issues. And then finally, install using R, not RStudio. That is something that it doesn't make as much a difference anymore as it used to. But finally, if you have a lot of difficulty on your system and you're getting really frustrated, I recommend to just launch an RStudio cloud environment. I'll show you what that looks like in just a minute, but essentially when you open up an RStudio cloud environment, you're essentially working with a functioning version of R and RStudio in the cloud. You still need to do all the same installations of different libraries. So you'd still need to run install packages, and you'd still need to load the package library, but it will be successful in a way that may not always be if the issue is with your hardware and not the software. And then finally, this raster, again, this link, I used this morning when I was installing these packages onto an RStudio cloud environment. So that is something that, again, if you're using that, that may be useful. So here, this is RStudio, what you're seeing right now. This is going to be will look almost identical to what we'll be doing throughout the workshop today. But as you can see, all the things here are set up in the cloud itself. So I'm going to open up a new workspace here. Essentially, it's free to sign up for an account. And then once you're in, you would start a new project. This is very potentially computationally heavy on my computer to both be doing a webinar and doing this. So I'm not expecting to work on this live because I don't want to sacrifice the quality of the webinar for that. Again, this is just a really useful tool for you guys to work with. And for example, if I wanted to load a library, I could either type it down here, or I could highlight this and highlight it like that and click run. Another way that I could do it is put my cursor on the same line as that library and on my keyboard type command return. And oh, well, normally that loads just that line, but it seems like in RStudio Cloud, it's reloading everything. So you'll find that there'll be a few differences, but the concept is the same. But that is essentially a very quick overview of just some of the common pitfalls when you're first setting up your system. But at this point, we're going to change presenters to Moksha, and she will take us through the beginning of our system. Oh, actually, one more note. I'm going to add this into the chat right here. So if you haven't already, this is going to be a little bit different than what Moksha just shared. I really recommend that you go to this site, and this is something else that I emailed everybody about, but please go to this site, click on that big green button code, and then download a zip file. The reason that's very useful is that once you've downloaded the folder and expanded it, you will see all the different markdown files that we'll be working from today. So we have 3 different presenters today. Each of us have a slightly different style of coding, but the goal is for you to see that there is flexibility within R. So if you'd like, if you open this up, you can follow along by simply running code that is within each of these areas. So for example, here, you would just run that, and assuming that you've already installed SF and TMAP, you'd be able to go from there, okay? But the other piece is this data folder. I recommend copying that and then pasting it into your new work folder. So in this case, we have a data folder here, and this is going to have all the data that you need to work with for the workshop, so that's very useful. If you are planning to use RStudio Cloud, then you should compress this data folder as a zip file. And I'm going to jump back here. And when you create this setup, essentially you would create your new workspace. And in this workspace, you could actually upload the data for the workshop. Be right there. So you upload that. I've already uploaded it, so I won't do it again. But then it will essentially bring all the data that you need for your session. So if you had trouble installing R on your own systems and you plan to use the cloud environment, that's a really nice backup. So with that, I'm going to stop and I'm going to switch over to Moksha. Thank you so much, Moksha.
Thank you, Maria, for that quick intro. I just want to check in. Can everybody see my screen? If you can, put it in the chat or in the questions, just let me know if you can. My name is Moksha Menghani. I work with Maria or at the Center for Spatial Data Science, and we work together to create this toolkit together with children. So Before we jump into the geocoding addresses section of the code, I quickly wanted to walk everybody through the RStudio. So this is the RStudio screen, and it generally has 4 panels. The layout of my panels might look slightly different than the standard layout because I changed it. I like to have the editor next to the console, but generally you would have 4 panels in your RStudio. This is the IDE, or the integrated development environment that we use generally to run our code. Most of the times you would have an editor in the first panel. In this panel, in the second one, I have the console, which is the R environment where the code actually will get executed. In the panel here, we have a bunch of different tabs. So history has all the history of the code that I ran before. So if you ever want to go back to a certain code that you ran, you can go back to the history and retrieve that. Files will just be your file locator, where you can see all the files. So I'm actually in the Intro to R4GIS folder. You can see I have these files here. Actually, if I refresh it, you'll see I have the data folder here. I didn't refresh it. Connections would be any external connections you have to the API or any other external interface. Viewer would be if you have any sort of interactive mapping, or you have created an HTML document using Art Markdown, PDF, any sort of work that is slightly more interactive or is an output that is not static would generally come into the viewer. So in this panel here, we have the environment. This is where the variables that we create in this art environment are going to be stored, or actually, this is where you can see them. Plots will have the standard static plots or any sort of mapping that you do. This is where the output is going to be shown of those. Packages. So these are the packages that Marina was talking about. I quickly want to show you that these are all the packages that are sort of installed on my system. But the ones that are checked are the ones that are already loaded into my environment. So when you start R the first time, some of these packages like the base package, data sets, I think utilities, graphics, all of these are automatically loaded into the environment. And that's just because R needs all of these basic packages to run the functions and the code that we want to put into the system. But if we want to install and load certain specific packages that we're going to need for our analysis, like in our case, the SF, the TMAP, and the tidy geocoder. So one method is, as Marina mentioned, and I'm going to type directly into the console. So you see install the packages showed up. I press tab, and now I can put the package name TMAP, and I press enter. That is one way to do it, or another way, and as you can see, it's downloading and it installed it. Another way to do it is to click the install button here, and then you can get it from the R repo, the CRAN, or you can download the zipped tar file onto your machine and then load that. So basically, if you click that, it will show you where can you read that downloaded file, and then you can install it using that, or you can install it using the CRAN. So let me quickly show you here. So for example, in this case, I've opened the CRAN page for tidy geocoder. When you go to this page, you can see this is the package source. This is where you can get the tar zip file. So you can download this on your machine, save it into a particular folder, and install the package using that. Or you can install it directly from the CRAN. And in this case, I'm just going to type in tidy geocoder, and then also SF, and then click install. It'll install any dependencies that is already needed. And as you can see, it's just basically ran that piece of code, and it's running it, downloading it, and it's going to install those. Okay. So now we have installed the packages. There's one thing I quickly want to show you. This is the help page. that you have, and this is very helpful. I particularly like to use it. So for example, if you want to know the syntax or any other details about the parameters that need to go into a particular function, or if you want to read more about a package, you can just quickly type question mark, and in this case, like mean function. I click that, and it'll show me the page of the mean function, and I can read about it. I can also go in directly to the package page if I want. Oh, so it didn't find the documentation for Tidy Geocoder because I haven't loaded it. But if I do double that, let's see, I think, yeah, it was able to find the page. So basically, if you have already loaded the package, in this case, the base package was loaded already into the system because it's a default package, the help will find it immediately with just one question mark. But in case you haven't loaded it already into the system, you would have to use the double question mark, and it will do sort of a global search for that package's help page and find that for you. And then tutorials, some of the tutorials we already shared with you, but you can also find other RStudio tutorials here, and you can go to that page and learn more about how to use RStudio and play around with the environment. Okay, so I'm going to jump on to our geocoding exercise. So what we're going to be doing today is basically read in a CSV file, which is chicago-methadone.csv, which includes addresses of locations that can prescribe or administer methadone for opioid overuse disorder. We're going to read in these addresses, convert them to geographic coordinates using a geocoding service. We're going to get their latitude and longitude coordinates, and then spatially enable them using a coordinate reference system. And once that data is spatially enabled, we're going to plot it and spit it out as a shapefile. So quickly, as Maria mentioned, we're going to be using for this 3 packages. The first one is SF, which we use to manipulate spatial data. Tidy Geocoder is the package that we're going to be using for geocoding addresses. There are a bunch of different packages in R that you can use to do this. I personally like Tidy Geocoder because it gives you a bunch of different options to use different geocoding services, and I'll quickly walk you through that. But this is the package that we're going to use today, and then TMap, we're going to use it for visualizing and mapping the spatial data. So you can basically load these packages into the library by typing, or just putting Command Enter, or using the run next to that line, or selecting that line and hitting run. So there are a bunch of different options to execute a particular piece of code in RStudio. I personally like to use Command Enter. Next thing we're going to do is we're going to set up the working directory. This is going to be the place where our input-output data is mostly going to be stored. This is going to be the place where any temporary files if created or any history files created will be stored. You can still specify to store or read in a file from a different library, but if you don't, then this is the default location where this environment is going to look for data. So before we start, I quickly want to show, I'm in the console to get working directory. I will tell you that I'm already in this working directory, but you can also set it up by using set working directory. And then the good thing in RStudio is that it can actually, if you press tab, it will tell you the path and you can keep on selecting that and reach to the final folder that we're looking for data, and then I hit enter. I saw a question, are there any shortcut differences in Mac and PC? There are a few differences. Generally, a command would correspond, command enter should correspond to control enter in a PC. But I don't remember the exact Windows commands on the top of my head. But you can also use run if you are having trouble directly running the code using the shortcut. So now we're gonna load in the methadone clinic data into our global environment. So we're gonna do that by read.csv, which is just a function to read in a CSV file. So it will be read.csv, and as you can see in RStudio, the function comes up automatically. And then I want to go into data folder in my working directory, and then read this file .csv. So as you can see, it was added to our environment. It read in the file and stored it into the methadone clinics variable. Now we can quickly look at the structure of this by using head methadone clinic. It is going to show me the first 6 rows of this variable. You can see the first column is X, just an ID. Then we have the name. Then we have the address, city, state, zip, longitude, and latitude. We already have this included in this file, just because in case we're not able to finish this exercise, or if you're having trouble, you have this data available for the further tutorials that Marina and Shunin are going to cover. So yeah. So now I'm going to quickly show you how can we use the tidy geocoder to geocode an address in R. So I have the sample address here, and I'm going to use the function geo. I'm going to say that rename the lat as latitude, rename the long output as longitude, and method use cascade. So this method function is method variable is something I talked about. That one of the reasons I like tidy geocoder is because you can choose a different providers or different methods to get the coordinates. So let me quickly show you the tutorial, the help, and walk you through what I mean by that. So here in the method, you can either use the census method or use the OSM. Or if you have access to these 2 commercial geocoders and have their API key, you can use Geocodio or IQ. So there are 4 different options that you can use to geocode a particular address in R. Or you can use cascade, which basically says that if the first method doesn't work, then use the second. If the second doesn't work, then use the third, and so on. You can also define the order of your cascade, like first use census and then use Geocodio. But in this case, we don't have access to the commercial geocoders. So the cascade will basically check for the census database first, and then it's going to look in the OSM geocoder to get the corresponding latitude and longitude for our addresses. So I'm going to quickly run this. Just let's give it a second. And then I'm going to show you the output of the sample. So as you can see, this is the address that we provided to the geocoding function. This is the latitude it gave us. This is the longitude. And here's the geo method it used. So because we provided cascade, it's going to tell us which method it used. If you specify to use census, this will be census for all cases. If you use cascade, it might be different for different addresses, and I'll show you that just in a bit. So this is how generally geocoding works. Now we can apply the same function on our big data frame of methadone clinics. But before we can do that, I just want to make sure that the data structure looks fine of that data frame. So I'm going to do that by using str function, which is effectively the structure of methadone clinics. So let's see. Okay. So here it tells you that it's a data frame, just 27 rows, 8 variables. And this is how each of the columns look like. The first variable X is an integer, name, address, state, city are all characters. And then zip code is an integer, and then latitude and longitude are numbers. The thing though is here, when we pass the address to the geocoder, it was all one single variable concatenated together. But here in our data frame, we do have the address, city, state, zip, in separate columns. So we need to concatenate it all together into one single address so that we can push it to our geo function. So I can do that by simply using a paste. So I basically convert address, city, state, zip individually to characters. So already address, city, as we can see here, address, city, state are already characters, but in zip code is an integer, so it will change it to a character, and then we can paste it all together. So generally a way to refer a column in a data frame would be to do something like use a $sign and then get the name of the column. So we can do as a character, this, and as you can see, it converted into characters. So I'm going to paste them all together, and then I'm going to show you how it looks like head. So we had all these columns already, and now we added another column, full add, which just concatenated all the fields, address, city, state, zip together. And now we can pass this column to the geocode function. So simply we got to do, so the geo function was generally works when you're using one address. If you want to use multiple, then you generally use geocode. And with the census method, you can do batch geocoding, and the limit on that is around 10,000. I think it is 10,000 addresses. With the commercial geocoders, it depends on what your package is with them. And with OSM, it just basically sends every single address as a single query to the system. So what I'm going to do is I'm just going to repeat that same code as we did at sample. So geocode, the methadone clinics data frame, the address is in the column full add. Change the rename the lat to latitude, launch to longitude, and then use the method cascade. And then I'm going to hit Command Enter. It's going to take a minute. Okay, it's done. Now we can view our output or our geocoded clinics, the data frame that it has created. Also, you can see it in the environment that it created geocoded clinics. You can view that. And now you can see we had all these columns. We added the full add, and now it also got latitude, longitude, and the geo method, which is OSM in certain cases, but in census in most of them. And we got this information here. I do want to say this is, in this particular data set, the geocoding ran fine without any errors the first time. That is not generally the case when you're working with a big batch of addresses. You generally need to clean the data. So say, for example, a street is named at ST versus a street, or an avenue is not named correctly, or there's a comma missing. Stuff like that can also sometimes give errors. So what I generally do is I run a first batch to see how many addresses got back fine, and then the remaining addresses for which I got missing values or the coordinates don't look fine, I basically clean them up a little bit and then rerun the geocoding process again. This is just a quirk that I need to work around when working with a big batch of addresses. So now we have the geocoded coordinates. Now we're going to convert that and spatially enable the data points and convert it to a spatial data frame. We can use that by using SD as SF function. So what you do is you provided the data frame that has the coordinates. You tell it which coordinates or which columns have the coordinates, so we have the, hold on. So basically here, we have the latitude and the longitude are the ones that have the coordinates. So I'm going to say the coordinates of longitude comes first, and then the latitude, and then I provide the reference system. In this case, we are using 4326. So we simply provide that, and I hit run. And that's it. It created into a spatial data frame. So if I do head of methadone SF, so as you can see, this is a tibble. It's just an object which has, which is a tidy object, which has more flexibility to use when we're doing a bunch of different computations. But for easy to see the data from easily, we convert it into a data frame. And then we can look at the head or the first 6 columns, and there we go. So as you can see, the latitude and longitude are no longer part of the spatial data frame, but we have a geometric column that has the point coordinates for each of the resource locations that we started with. Now we can quickly plot it using TMAP. We're going to set the mode with view, which is the interactive viewing mode, as you can see. So the way the TMAP works is that with TM shape, we tell which object do we want to use as the layer. How do we want to plot that object? So like, do we want to use dots, lines, polygons? So in this case, dots. And then what is the base map that we want to use? We provide that and then do Control Enter. And because this is the interactive map, it actually came in Viewer. And as you can see here, this is what the map looks like. This is where the layer, you can select, unselect it. And then if you click on it, you're going to see all the information about that particular resource location is here. So we have this, and now, sorry. We have this, and now we can write this methadone SF spatial data frame. Oh, you can also check the class of this by using class. And then you can see it's a SF object, and it is also a data frame. It is also a table, and so on. And now we can write this to a shapefile by simply using write_SF, and then the name of the object and where do we want to store it. So I'm going to put it here. I'm going to put it here. And then if you click on the data, you can see we added the 4 files here, which are the shape files. So that's it. That's how the geocoding process works. I'm going to pass it over to Marinia for the next section of like doing buffer analysis and running the access metrics. Just a sec, I'm trying to pass it over. Okay.
Moksha, I think I flipped it over.
Okay, perfect.
It's all good. Awesome. Fantastic. So hopefully that was really exciting for some of you, because I think that batch geocoding is almost always, I mean, it can be very challenging, and depending on what geocoders you have access to, right? It's just a really phenomenal service. And so at this point too, you're probably wondering, you know, why am I geocoding methadone clinics in Chicago? Well, remember, this whole toolkit is about generating opioid risk environments, or trying to better understand that. So methadone is an evidence-based medication for opioid use disorder. We call that MOUDs in this workspace. And one of the things that we're going to be doing throughout this toolkit in our workshop today is to try to really investigate different aspects of that. So now we have different methadone clinics that have been geocoded to Chicago. The next step is what might be reasonable access to that, okay? Obviously, access is an extremely complex topic. I personally like the Thomas and Pachansky definition of access, which is, you know, multidimensional. But because this is a quick toolkit, we're gonna mainly focus on well, the first aspect would be spatial access. Before we dive into kind of more complex access metrics, it can be helpful just to start with a buffer. And again, this is not necessarily the final and a final access metric for a really sophisticated spatial analysis. But oftentimes, especially when you're working with a multidisciplinary group, this is a quick, easy way to kind of visualize the data and get some good concepts going. So the goal of this next chapter is to develop a buffer service area of 1 mile. Why do we choose 1 mile? 1 mile is considered a generally walkable area. It's commonly used in food desert research, especially in urban environments, to again approximate how far would you have to travel to a grocery store in a way that would be reasonable. So 1 mile is considered a reasonable walking distance. We're going to use the same metric for methadone clinics because especially at early stages of treatment for opioid use disorder, it's really important to have, in some cases, daily or weekly access. Again, the spatial dimension of access in this case is really important. So if you're interested in following along, I'll be kind of doing a bit of a jumble of both chapter 3, buffer analysis, as well as chapter 4, where we're going to link some additional data. The goal of this first chapter is, again, to generate some access metrics. In order to do that, we have to transform coordinate reference systems so that we have a proper coordinate reference system to generate a buffer. We'll do a little bit of buffer operations. And then finally, when we shift to chapter 4, we'll be reading in COVID data. So this is data that was downloaded directly from the city's data portal. At this point, it's not up to date. It's, I think, 1 or 2 months old. But essentially, we're trying to identify where are areas in Chicago that have exceptionally high COVID, that are being disproportionately impacted by COVID. And so our goal is to identify vulnerable populations within those areas of persons with opioid use disorder who need to access medication, but may be impacted by lockdowns or or by the actual community transmission of COVID itself. So that being said, as I mentioned before, you are welcome to, so if I open up this folder, you can either look at the original R Markdown files where you can grab that information. In this case, I've created a new folder on my desktop, and this new folder has the folder called data. I just drag and dropped it into this environment, or I didn't drag and drop it, I actually copied and pasted it here. I have a version here that we'll be working from, but okay, so let's start here. So in this case, I have opened up RStudio. I have opened up my demo file, which is just a bunch of empty code. There's not much in here. And this is what I see. So you'll notice right away that how my RStudio looks like is a little bit different than Moksha's, and that's okay, right? So when we're working with programming interfaces, it's best to find a system that works for you. I like to have the console underneath, and I like to have a working script. So in this case, if you want to create your own working script, you can go to File, New File, RScript, and save, demo workshop. You save it within the folder that you want to, that includes the folder for your data. That's really important. So you could potentially work from that as well. When I'm setting this up, one of the first things that I'm going to need to do is set my working directory, right? Because Moksha already did that in hers. I have to do that in mine. So the way that I do it is if you go to this files section, it generally starts in your home screen. I like to navigate to where my information is. So it's under desktop, it's in this folder. And then a nice little tool in RStudio is this little icon. If you click on more, you can click here, set as working directory. And then I like to just copy and paste that into my script that I'm working. Okay, so we don't need to run that again, but it is there for you. All right, so next step, I'm going to ask you guys to load some libraries. So first we're going to load SF if you haven't already. I'm assuming that you have, and I'm also going to load TMAP. Okay. And we can see that that worked successfully. So next I'm going to load some data. There's 3 different data sets that I need to start with. These 3 data sets will be, you'll be able to see them at the very beginning of the first, the chapter on buffer analysis. But first I need to have my methadone clinics. So I'm gonna call them Met Clinics. And notice that in R, you can use this little arrow. You can also use an equal sign I've also seen people do it this way, the arrow in the opposite direction. It's a pretty flexible language for some things. And then I'm going to use my function stread to read in my data. So I have written down here what that is, but if you're not sure, you go to your data folder and you look it up. So here, methadone underscore clinics.shp, it reads it. Okay, so it's reading it in as a shape file. I'm going to read in my areas, st underscore read, and same thing. So that's going to be my data folder, Chicago zips. And this, I believe, was a shapefile that was directly downloaded from the city open data portal. Later, you'll find in the next mini tutorial that there's actually a lot of different ways to do this. Okay, and then finally, I'm also going to create, pull in a city boundary file of Chicago. The reason I'm doing that is because I actually want to make some pretty maps. So in order to make some pretty maps, it really helps to have a boundary file that you can use to kind of focus the attention of where the map will be within within R. So I'm doing this. You'll note here that this is a GeoJSON file, and you know, SF doesn't matter. SF also stands for simple features. For those of you who've ever worked with PostGIS in the SQL world, it's the same concept. And simple features is a really nice standard for, it's an international standard for geospatial data. So for those of you working with ArcGIS, the same standards apply. And we work a lot more with SF instead of SP. SP is an older framework for R, so that's one of the reasons that, yeah, we can talk about that later in questions and answers, but yeah. But starting here, we have our 3 data sets. Something that you might enjoy is you can already start making some simple plots just based on what you've loaded in. So for example, if I want to plot my clinics, I can use a base R function plot. And because I've loaded in SF, it will create basically a plot of every single variable that you have in your data set, right? So I think, well, actually, no, the first 8. So if I want to look at the first couple of, the first few rows of the data set, I use my head function. And again, here you can see quite a bit of information. The geo method here, you can see exactly which addresses were geocoded in different ways, so on and so forth. But what I'm really interested in is making a more interesting map. So Moksha already covered some of that, but let's say I want to add zip code areas. And technically, I know you guys are GIS folks, there's zip code tabulation areas. So, you know, forgive us for calling them zips by short. But outside of the GIS community, folks are not as caring. Okay, so first we're going to add a map of our areas. So this is going to be a map of the zip codes. Notice this is not a fancy interactive map. This is using the default setting of TMAP, which is plot. Okay, and this function right here, alpha, is adjusting the transparency. So you can see it's a little bit lighter or darker. I really love using the alpha function because it can add a lot of nuance to the maps that I make, okay? So here I'm going to overlay on top of that the methadone clinics using, and when you're visualizing points, TMAP will either want you to use dots or circles. So circles will be a graduated symbology, but dots is going to be your default. So you can either just have it like this and you can see our tiny little dots here, or you can add a little bit more panache to it. So let's add a different size, and let's say the color is going to be equal to red. Okay, so now we can see a little bit more detail. Next step, I want to make buffers, so I have to deal with coordinate reference systems. So you've probably been wondering, how does R deal with coordinate reference systems? Well, your first favorite function will be st_CRS. All you do is call in the clinic that you're interested in, and it will tell you exactly what the metadata is for the coordinate reference system. So here it's 4326. WGS 1984. So while that's standard, distance is measured as degrees, not feet or meters or something like that, that's a little bit more necessary. So what we need to do is switch into a different coordinate reference system. Let me go over here. If you're not sure what coordinate reference system to use, then Google it. When we're dealing with coordinate reference systems in R and just other coding languages, I really recommend that you look up or become familiar with the EPSG. This is a kind of an international standard, and this ends up being our dictionary for identifying different things. So let's say I want to look for an EPSG of Illinois in feet. That's what I'll Google. And right off the bat, the first thing listed is EPSG 3435. This uses NAD 83. It's Illinois East, and so that ends up being exactly what we want. So next up, I'm going to create a new object called CRS new that's going to essentially store a coordinate reference system of EPSG 3435. And I really like doing it this way. Sometimes you kind of get away in QGIS or ArcGIS by just clicking from a wide list of other reference systems, but in this version, you're really encouraged to get close and personal with your EPSGs. So now I'm going to essentially create, just for good data practice, I'm going to create a new MetClinics object with my new coordinate reference system. And I'm going to use the really powerful function ST_transform to take my MetClinics and put those in, recast those into a new coordinate reference system. So I do that. It works pretty well. I'm going to copy and paste that and do the same thing for areas. Oh, that it worked, but it's not very useful because I misspelled areas, and I'm going to need that later. So I've done both of these. Now I'm going to create buffers. And you're probably wondering, like, how in the world do you remember all this? I don't remember it. I have lists of existing text like this. So I have our markdowns or coding snippets or tutorials from other groups. You start to kind of develop your own repository of different coding snippets that you've seen from other places, right? And in many cases, some of the best most proficient coders of R and spatial analysis are the ones who have seen the most code. So a lot of these are not things that you're going to just know off the top of your head. You'll find it in other tutorials like what we're doing today, right? And then further than that, you will, when in doubt, you can also go to the documentation itself on R. Granted, a lot of the documentation is not done very well, so it can be kind of confusing. So I always like to again bookmark tutorials, other coding snippets that work. At the very end, we'll also share some more different resources like the Geocomputation in R, text by Lovelace et al. That's a really great one, but so on and so forth. But back to what we're doing here, now we're going to use the buffer function. And again, you'll notice that all of these start with ST_. That's the same exact standard that you'll see in PostGIS and other languages. So really exciting. We're going to create a buffer for MetClinics, I believe. Yep. And we want to do that in the function. So let's say we did this for our previous one. And I'm going to do this for 5,280 feet, which is equal to 1 mile. So if I do this, I get a warning message saying ST buffer does not correctly buffer longitude latitude data. So I may still get a response, but it's going to be pretty inaccurate, right? So if I get an error message like that, the error message is there to help me. It's not to make me panic. So I'm going to rerun this, and I don't get an error anymore, which is pretty neat. Okay, so at this point, I'm going to copy and paste the previous map that I generated. Here I'm going to paste it. And then on top of what I've done here, I'm going to add a shape, a new layer of, let's see, the buffers. So I'm going to add that right here. This is not, buffers are not dots, so I'm going to use a different function. In this case, it'll be borders. and I'm going to call the borders blue. I'm going to color them blue. Excuse me. Okay. And beautiful. We have buffers. They look like they're plotting correctly. This is a point that can also often cause anxiety if there's anything that has gone wrong with your projections. If you cast the points in the wrong projection, or if you cast the new buffers and something went off, if you have buffers that are the size of your room, instead of this tiny piece of the screen, that's a sign that something's wrong with the projection. So that's where you'd want to go back. But note here too that this Met Clinics is in a different projection, but TMAP and R still know to kind of put that all together. So if I want to redo this, I'll get exactly the same map. Okay, so you can start to make this look even prettier. We can start to change the sizes of the different pieces here. You can, let's see here. We're starting to run a little bit over, so you can try on your own. There's a couple tips in the different chapter that we've included for yourself. But looking at what we have here, so while this is interesting, the concept of service areas can be useful as well. So service areas are essentially kind of a binary, like either this area is within a 1 mile Euclidean distance of a methadone clinic or it's not. So for something like that, you might want a union, and a union merges all the buffers together. In order to do that in R, we use an ST union function. So here we're going to use our buffers, and now you can try visualizing that. So I'm going to copy what I did up here, and I'm going to visualize that instead. Okay, so here you can see that we have something nice happening. I can change borders to fill the inside. It's going to look kind of ugly because of, well, it looks a little ugly here, but what happened, this union of buffers has covered my clinics. So when that happens, you can just kind of flip things around, right? So let's try what that looks like. And now they're overlaid again in a much more effective way, right? At this point too, you can start to generate different types of buffers. So instead of creating a 1 mile buffer, let's say we want to do a little bit more sensitivity work and try a 2 mile buffer as well. So here, 10,560 feet should be 2 miles. And actually I just wrote over this one up here. So I'm going to rerun that one so I don't rerun it, don't create an issue. I'm going to create or write this buffer into the name 2 miles or 2M, which makes a little bit more sense. And then at this point, let's see, I have this really big and beefy massive option here that might be a little bit easier to run this way. Okay, so we're looking down here. We're looking for a nice area. Let's try this one. Okay, so we're gonna copy and paste, and if you don't necessarily have to download the R Markdown to do this. If you go to buffer analysis, and at the very end, for any of these things, if you hover over any of these, there's a little option to copy and paste and so on and so forth. So that's also another option. So here, let's see, I'm going to copy that and I'll paste it here. Here, I'm going to do a little bit more work. So here, I'm going to still map the zip code areas, but I'm going to visualize this within the city boundary of Chicago to kind of focus the area. This B-box feature is really phenomenal. We can talk about that later if you're interested. I'm going to also visualize the outline of the city boundary. I'm going to add my 2 mile buffers and color them gray. I'm going to take my 1 mile buffers, color them in a darker gray. I'm going to take my clinics and let's see if this works. All right, so here you can see this map on the right-hand side. What's really nice is that you can zoom into it. And with TMAP, this is where you can also add things like scale bars, legends. there's a lot more information. So if you're interested in this, I recommend looking at the TMAP documentation. But there's, TMAP is never going to be the same as ArcGIS or QGIS, but for quick and easy maps that are good enough, you can do quite some good work. And I should say that there is quite a lot of really fantastic cartography that is happening out there, both with TMAP and ggplot extensions, but feel free to check that out. And so I'll just run through a few more things in the last 2 minutes before I pass things over to Chinwing. So at this stage, let's say that we're really, again, interested in how COVID is interacting with the data here. So here I'm going to use a read.csv function. There are many, many, many different ways to do that, but that is what I'm doing here because this is quite a long name. I'm going to just copy and paste over here so that it is a little bit more reasonable. Okay. So we've read in our COVID data. If you want to look at what the COVID data looks like, you can see that here. So there's a lot of information here. The way that read.csv does, it transforms very long header names by epidemiologists who are not following best data data practices for GIS systems. So there's a lot of spaces in the headers. So this kind of collapses all of them to different sorts of periods, okay? Which can be a little frustrating, but it's something that you need to get used to, okay? So here we're going to subset the data. And there's many different ways to subset the data, but here I'm going to use this bracket format. The bracket, essentially, the first line will be taking all of the, let's say, rows, columns. So if I don't put anything into the first slot here, it's essentially saying I'm going to take all the rows, and for the columns, I just want zip code, and I want case.rate, ... I think the cumulative. And that should, and this is something that I checked out before. I looked at this and I tried to understand which one of these here, yeah, case rate cumulative. There, it's right there. So this is essentially cumulative case rate up to this certain point. And I believe this again was pulled around the end of October. So we grab that data. Next step is we're going to merge the COVID data. I'm going to create a new field called GeoID10, and you probably know that this is going to match the same field as my zip code data set. Okay, so it helps to, when you're creating a new piece of information like this, that it's going to match. So I've got COVID. I'm going to take my zip code field and rename it or recast it as a character, and then cast that new character zip code ID to a field called GeoID10. And at this point, I am going to create a new document or a new object called zip merged. And all right. So this is essentially, we're taking the zip code areas, we're going to merge the COVID data, and we're not going to go over keys because as GIS folks, you probably are already familiar with that. We're going to merge these based on, again, the GeoID code. So on the zip code side of things, it's called GeoID10. Here we've recast zip.code as GeoID10, and we're ready to go, okay? So I can copy and paste this if I'm not sure. And let's look at what that data looks like. And here we can see that we have all of the zip codes, but in addition to the zip codes, we also have case rate cumulative, and here again is a zip code that I've pulled in from this other piece. All right, so finally, I'm gonna just create one map of this and then pass it over to Chinwing. So here I'm taking my zips merged. I'm going to use a different function here called polygons. Polygons are going to actually essentially give us the ability to generate core path maps. And this is going to be a really nice segue to what Chinwing will be talking about. So first, we say which variable we're interested in generating a map of. we're going to tell it what is the data classification style that we want. So here I'm going to use quantile, which, as you know, is probably not the best method, but that's where we're going to start. We're going to use a palette, a color palette called Boopoo. After this ends, there's many different ways to figure out which R code palettes are available to you. And the easiest way to find that is just by Googling it, but we can also kind of go from there. Okay. So here, this is going to get visualized in just a second. And as you can imagine, from this map, you can now add the other information that you had up here. So let's say I want to add clinics and buffers. We can try that just by adding that right here, and let's rerun that. Okay, and so from here, I encourage you to kind of keep on going through what you see in both the buffer chapter as well as the contextual data chapter. This is a super fast overview. But here, again, you can see that there are several areas that have extremely high COVID case rates on the west side, both up here and down here, that are outside of walkable areas of methadone clinics. And obviously the other piece is, are all of these methadone clinics open? So if there's a closure of one of these clinics due to the pandemic, you can kind of recast this map accordingly. So with that, I'm going to stop and pass over to Chewing in our marathon of work here.
Hello.
Yep, we hear you. Yep, we hear you. Go ahead.
Okay. Hi, everyone. This is Chen Ling. I'm a postdoc working with Marinia. And I will walk through some parts in chapter 5 and chapter 6. Here we will want to incorporate some data from the American Census survey, and then we can look at how those data relates to the access metrics Marinia just correlated, and we can do some interesting plotting together. There are several ways that we can do the we can download the census data together with the geometry feature. I will walk through both approaches quickly, and also we will use Chicago as an example. Before we start, we need to load some libraries we will use together. As what Marinia and Moksha did, we need the SF library to read and write SF or spatial object. We also need the tidy census library. This is a library that we will use to download census variables use the ACS API. Oh, by the way, so before we doing this, we need to, everyone needs to get a API from the ACS. And I think in the email sent by Marinia before the workshop, there is a link where you can acquire an API. We also need the tidyverse library. The tidyverse library is really an amazing library in R. It makes the data manipulation and cleaning extremely easy, as we will see later. We also need the Tigris library. This is a library where we can download the census tiger shape files. And finally, we need the TMAP library. Okay, so I will load this together. And my console window is here below the code window. This is like what Marinia is setting. And also one thing to note here, so all the code that's starting with a pound sign, that's a comment. So you can write whatever you want here, and that's not a code. And you can also see that one thing that's really good with RStudio is that you can see the color of the coding are different from the color of the comments. Okay, after we load these libraries, we need to enable the API. And you can use the census underscore API underscore key function to load your to enable your API, and you put your API here. and then say star equals to true. And for me, because I've already enabled my API previously, and I just want to check if my API is still working, then I can use this function called system get environment, and I want to look at the census API key. So if I run this, I can see this is my API. Okay, and the next thing we will do is to explore the variables. There is a function called load variables. And in this function, we will tell it that we want to see the American Community Survey of 2018, and we will use the 5-year estimates because that's more reliable than the 1-year estimate. And then if we run this, we can see now we have an object called variable names. Let's see what the object looks like. So in here, the head function shows us the first several rows of the data frame. So here we have 3 columns, name column, label column, concept column. Then you can try to find out what variables you want from the ACS survey. And to see all the data, we can also use the view function that will open a new window here. Will show you all the array rows in the data frame. Okay. Okay, and we will start with the first approach, which is to download the census data with geometry feature together using tidyverse. To do this, let's try to try something that we want to right now. Let's say we want to download the tract level data from Illinois. So let's say we call it tract Illinois shape file. It's not exactly shape file, it's just an object, and I name it as tract IL shape. And it's actually, as we will see later, it's a spatial object. And we will use the function called getACS. And one thing which is very helpful regarding RStudio is that once we type the function name, we will see what arguments is needed for this function. So let me try again. So getACS, and then you can see in this pop-up window, you can see what arguments you need to specify for this function. So the first thing here is geography. For geography, we need to tell what level of data we need. So here we will say we need tract level data and what variables we need. And here I will just copy and paste because it's a long one. Okay. Okay, so these are the variables we want to download, and these are variables that about some demographics for each tract. So the total population, the Hispanic, non-Hispanic, white, African American, and Asian. And we can check all these variable names again back to this data frame. This is like a metadata we downloaded before. Okay, and also we need to specify what year we want the survey from. So we want the 2018 survey data, and we only want the Illinois data. So we say state equals to Illinois. And also one cool thing here is that we can specify that we want to download the geometry data, geometry feature with the data together. So we will say geometry equals to true. Let's try this. And it may take a while. Oh, it finished. It's quick. It's quick this time. Okay, now we do the download, and let's see what this data look like. So this is a simple feature collection. So it's an FSF object. It's a multi-polygon data, and we got the geo ID, the name, and we here we can see that we get all the variables, and each variable represents is represented in one row. But we know that we are more used to the a data frame where each variable is a column. So right now it's a long format. We want to transform it to a wide format so that the later analysis could be more convenient. To do so, we will use some feature by the tidyverse package in R. So we will say we will need to do some manipulation for this object. And what manipulation we will do? We will first select some variables that we need, including GeoID, name, variable, and estimate. We will not pay attention to the MOE, which is margin of error here. We select those variables from the data frame, not for data frame, this is a spatial object. And then we will do the spread function. The spread function is to change the data format from a long format to a wide format. So we will say we will do the spread based on the variable, because the variable column tells us what variable this row represents, right? Variable, and we will do the estimate because the estimate column includes the numbers, the real values of that variable. And also we will do some calculation. So here, I'll copy and paste again to save some time. Here we will calculate some new variables using the variables we download to calculate the percentage of Hispanic, the percentage of white, the percentage of African American, Asian, etc. Okay, and the mutate function here actually help us do this thing. And then finally, we will select only those variables we need again. So that's GeoID, and then all those new variables we created together with the total population variable. Okay, and let's run this. And now let's see what the data looks like. So now we have a spatial object where we get each row represents one tract, and we have information regarding the total population, the percent of each race for the tract, and it's in a way that we can save out as a shapefile, etc. Before going to the Chicago example, let's do this in another way, which is we can download the census data from the function getACS, and also we can download the census boundary using the Tigris package. So we do this thing separately, and then we use the merge function to put them together. Okay, and now let's try a different example where we will use the zip code level data. So let's say we will create an object called ZCTA-DF. DF represents data frame because now we will not include the geometry feature. Okay, so we again use getACS function, and the geography now equals to ZCTA rather than tract. And then variables, let's try some different variables. This is a variable that measures the per capita income for each zip code level. Okay, and then we will still use the year of 2018. And now we will say we don't need the geometry. So we will say geometry equals to false. And we will use this tidy verse function to combine the several codes together. So we say we first download this data, and then next we will select some variables that we need. That's GeoID, name, variable, estimate. That's exactly what we do previously. And also we will do the transforming from long format to the wide format. Again, spread variable estimate. Okay, you may notice that here I'm not specifying any state here because right now we are downloading the national level data. And let's see what the data looks like. Had ZCTA-DF, yeah. Okay, so right now we see that each row represents one zip code area, and we have a column called per capita income, which represents the per capita income for that zip code area. So we finished the first step of downloading the census data. Now let's download the census boundaries through the Census API. So now we will create a new object called ZCTA shape, because we want it to be a spatial object rather than just a data frame. And we will use the function called ZCTA as. This is a function that we can use to download the boundaries. And we will use the year of 2018 and CB equals to 2. This is a really useful argument. By specifying CB equals to 2, it will give us a generalized boundary, which is not too massive. So for example, I can use, I think Moksha mentioned this, every time we get confused about what one argument means, we can use a question mark and then type the name of the function. And then here you can see the information of this function. And here you can see what it means by specifying CB as true. So if you don't specify CB as true, the default is false. That means it will give you a detailed file, which is massive, so it can get really big. Okay, so now we get this spatial object. We want to combine this spatial object together with this data frame so that we can have both information. We will do this, use the merge function. And in the merge function, the first thing we need is a spatial object. And then the next thing is a data frame, which includes the variable we are interested in. And then we need to tell what ID we need to use to do the merge. So the by.x is the ID or the key for the first thing you use here. And normally what I do here, I will check names, which is basically what are the column names for the CTA shape to get the key variable names exactly right. So this is the variable name that we will use as a key for the CTA shape spatial object. And then we also need to specify by.y. Then I will check the column names of the ZCTA df. And here it's called GeoID. Okay, and then I will also specify all.x equals true. This means that I want to keep all the rows in the x. This is the ZCTA shape object, even though the ZCTA df may not include this row. Okay, and also I only want to include those columns that I really need. So I will include GeoID 10 name and then per cap income. Okay, let's see whether it worked. Okay, I got an error message. This could happen because I forgot to clear my environment. So one thing I could do is that I can clear my environment, okay, and then redo everything again. Okay. Okay, now it works. And let's check what the data looks like. So now we can see that this is a spatial simple feature collection with 6 features and 3 fields. We have each row is zip code, and also we have the information of per capita income. Okay, next we will look at an example where we only want to see the Chicago, and then we want to plot out the per capita income for the Chicago area. To do this, we need to download the required data set for the entire country, which we already did so. And then we can filter the relevant zip codes by overlaying the downloaded data set with the geometry feature of that region. So basically, we need a Chicago boundary data set. It seems that we are running out of time. So instead of live coding, I'll show you this one. Previously we have already got the ZCTA shape spatial object. It includes the per capita income, but this is national level data, right? So we need to do the second step, which is to reading the city boundary file from for Chicago. And I think Marinia already covered this. So we read in the boundaries _ Chicago.geojson. This is a boundary for Chicago. And then one important thing here is that we need to set the same CRS for both shapefiles so that later we can do the intersection correctly. So here we are setting the both shapefiles to have the CRS as 4326 using the powerful function st_transform. After this, we can use another powerful function, which is st_intersection, and this can help us only keep those zip codes that intersect the Chicago city boundary. Remember, this is a national level data. This is a Chicago city boundary. So after doing this, now in the object called zip Chicago shape, we only have the information for Chicago regarding the per capita income. And we can look at what it looks like. So we have the geo ID, name, per capita income, and also the geometry information. We can use write_sf to write this object as a shapefile to the data folder. We can also use a base R function to plot it out. This is the geometry. Right now, we only have the Chicago, not the national level. And we can also do some fancy plotting using tmap. This is just plot out the geometry again. But here, we can use a tmap to plot out the per capita income distribution in Chicago. So here, we are saying that for the layer using zip Chicago shape, we want to use the variable called or the column called per capita income to do the filling. And we have a title called per capita income. And in the TM field, you can specify what style you need. So you can specify it as a quantile map or fixed bin map. There are a lot of options there you can use. And also we can specify other things in the TM_layout to make it prettier. Change the legend title, the main titles, the title size, etc. This is a fixed bin, and also this is a quantile map example. Okay, I think I'll stop there and then I'll give it back to Marinia.
All right, thank you. And actually, this is because we're at time, but the three of us are happy to stay on for a few more minutes if there's questions. I hope that this was helpful. Here, I'll switch to video at this point. Is there anything? We've been trying to monitor chats and questions down here. But yeah, let us know if there's any final notes or questions, and we're super excited to have you all here.
That was really great. So many really helpful tips about how to manage this, and super powerful. I know it was fast for you to cover all of that. It was an ambitious workshop agenda, but I'm so glad that we have the recording that we'll be able to share with people too, so that they will be able to go back and follow through clearly on any of the specific steps that they might have missed going through.
Definitely. And I mean, that's the toolkit is there for anyone to kind of go through step by step as well. And again, when in doubt, you can always go back to the R Markdown files at that and just run each line as you're
Yeah,
learning.
thank you so much for providing those. Thanks to all three of you so much for doing this with our UCGIS audience. If there aren't any questions, let's see. There is one quick question. Maybe we could address this. Lena, or I'm sorry, Marini, if you want to see the question here from Lena, if there's a.
Yes, definitely. So yes, so in this case, we wrote to shapefiles, but with the ST-Write, so I would recommend looking up ST-Write. So for here, I'll include what I would. Can I send this to all? Yeah. So I just sent. So for specific questions like that, first you should always assume yes, it's possible. ST is kind of a very neutral coding framework within R, and it recognizes shapefiles and GeoJSONs, and there's a big GeoPackage community. So to look for a specific coding, I recommend use the function that you're interested in. So ST-Write with the parenthesis, and then type R, and then type GeoJSON, and you'll find like 5 or 6 answers to your questions right off the top of the bat. The other option is to look into the documentation directly, but yes, it's definitely possible. Hopefully that helps,
All
Lena.
right. Excellent. Okay, so thank you again. Thanks to all of the participants who've been following along very attentively throughout this. We'll wrap up this workshop right now, and we will be sending out the link to all the registrants in the next day or so. And thank you all very much for your attention. Stay safe out there.
All right, thanks all.
All right, bye-bye.
Bye.